In this video, I'll show you how the product rule works. The product rule is used when you want to find the derivative function of a product of two other functions. Here is an example of a function, h of x, that is the product of two other functions. The way I've written it, it should be pretty clear what the formulas are for these two other functions. F of x is the polynomial function 3x squared minus 2x plus 7, and g of x is the exponential function 3 to the x. And if I asked you to find the derivative function, h prime of x, your instinct would be to do something that, it turns out, isn't correct. You'd first think that, well, the derivative of f of x is 6x minus 2, and the derivative of g of x is the natural log of 3 times 3 to the x, and then your instinct would be to multiply those to get your h prime of x. But unfortunately, your instinct would be wrong here. So let's look at what's happening a little differently. I'm going to think about this in terms of area. So I'm going to represent f of x as the length of one side of a rectangle, and I'll represent g of x as the length of another side of the rectangle. So now h of x represents the area of this rectangle, and then h prime of x would represent how quickly the area of the rectangle changes as we increase the value of x. Now, if we increase x by a tiny amount, then f of x will also change by a tiny amount. In the past, we've called this delta f, but when the change in x is small enough, we write it as df. Similarly, as we increase x by a tiny amount, then g of x will also change by a tiny amount, which we'll write as dg. Next, let's think about what happens to the area as we increase x by a tiny amount. As x increases, f of x changes by df, and this changes the area of the rectangle. Similarly, g of x changes by dg, and this also changes the area of the rectangle. Next, we can think about how much the area changed by. So, as x increases, then the area changes by delta h. And if the change in x is small enough, then we call this dh. The area that we got from the change in f is df times g of x, and the area that we got from the change in g is dg times f of x. And you might notice that there's sort of a little notch missing from this rectangle. It turns out that when the change in x is tiny enough, then the change in area due to that little notch is so infinitesimally small that we just end up ignoring it. Basically, in the limit, it goes right to 0. So now, the total change in area would be the sum of these two areas. And if we remember that the derivative of h is dh dx, then we can divide each side of the equation by dx. And then we're going to do some algebra. So we're going to rewrite the fraction on the right side of the equal sign. Then we're going to do a little more algebra. And now we have dh dx, dg dx, and df dx. And these are really derivatives. So we can rewrite this whole thing as the derivative of h of x is equal to the derivative of g of x times f of x plus the derivative of f of x times g of x. So now let's go back and look at the original example. Here's the original example we saw, where we wrote h of x as the product of an f of x and a g of x. And we also previously figured out that the derivative function of f of x is 6x minus 2, and the derivative function of g of x is the natural log of 3 times 3 to the x. So we can put this all together to find that the derivative function of h of x is the derivative of g times f of x plus the derivative of f times g of x.